Hello and welcome to section 10.6. Today we're going to talk about the alternating series test. First we'll define an alternating series, and then we'll talk about our flow chart and determining absolute and conditional convergence. We've seen those definitions before, but I'm going to remind you of what they are before we do those tests. So an alternating series is one where the terms alternate between positive and negative. So they're going to go plus, minus, or they can start with a minus, but then they'll go plus, minus, plus. What you can't have is minus, plus, minus, anything where the terms don't strictly alternate between positive and negative. So let's look at these two examples here. This first one looks like it might be alternating because it's got a -1 to the n in it. But upon further reflection, if we rewrite -1/2 to the n as -1 to the n over 2 to the n, and then we combine exponents, -1 to the n times -1 to the n is -1 to the 2n, we see that this series is not alternating because there are no negative terms at all. -1 to the 2n is always positive. This is just 1 over 2 to the n, which is 1 plus 1/2 plus 1/4, ... There are no negative terms. It's definitely not alternating. All right, the next one doesn't look alternating, but actually it is. Let's write out some terms and see what's going on. When n is 1, cosine pi over 1 is -1. When n is 2, we've got cos 2 pi, which is +1 over 2. And when n is 3, we get -1 over 3 because cos 3 pi is negative. And then it'll go plus 1/4, ... So we could rewrite this actually as the sum n equals 1 to infinity of -1 to the n times 1 over n. And that is alternating. The terms go minus, plus, minus, plus, minus, plus. So, if you have an alternating series, you can use the alternating series test to determine if it converges. So, if you look at the sequence of just the positive terms, so leave off the -1 to the n or the -1 to the n plus 1, and just look at the sequence un. If it satisfies these three conditions, then the series converges. So the limit of the UNs has to be 0, all the UNs have to be positive, and the UNs have to form a decreasing sequence. Remember, for showing a decreasing sequence, if the numerator's fixed and the denominator's increasing, like 1 over n or 4 over n squared, those are obviously decreasing sequences. If both the numerator and the denominator are increasing, like n over ln n, then you would have to show that that sequence is either decreasing or not decreasing. That would not be obvious. All right, one more comment on the alternating series test. If condition 1 fails, go ahead and use the divergence test because the series will diverge. Okay, so let's try the test out. Let's use the alternating series test on this infinite series. And so we're going to use AST with our UN equal ln n over n. That's the sequence of terms without the plus minus. Okay, so condition 1, the limit as n goes to infinity of ln n over n. Now that's infinity over infinity, but we know it's 0 by theorem 5, section 10.1. That's one of the limits we're allowed to use for free. 2, all the terms of the sequence are positive. So I'll put a check mark by 1. Check mark by 2, that's true. And then 3, we need to determine if ln n over n is a decreasing sequence. Now that's not obvious because the numerator is increasing and the denominator is increasing. So to show that's decreasing, I'm going to let f of x be the function ln x over x, and I'm going to show the derivative of f is negative. That will show that f is a decreasing function, which means the sequence will be decreasing. So f prime of x, we have to use the quotient rule. The derivative of the top is 1 over x. 1 over x times x is 1. And then minus ln x times the derivative of the denominator, which is 1, over the denominator squared. Now, that needs to be negative. And that's going to happen when ln x is bigger than 1. So that will happen if x is greater than e. Now, e is about 2.7, so that's fine. If the first few terms don't behave, then you can go ahead and start the series at 3. That won't change the fact that the series converges or diverges. So up in the test, you can see I wrote down on condition 3, it's okay if the first few terms don't behave. You can just ignore them. So condition 3 is met, and so the series converges by the AST. All right, here's an example of what happens if condition 1 fails. So we're going to use AST with UN equal to the sequence n over n plus 1. So leave off the negative 1 to the n. And condition 1 is that the limit as n goes to infinity of n over n plus 1 should be 0, but it's not going to be 0. It's infinity over infinity, so divide top and bottom by n, and we get 1, which is not 0. So that doesn't mean the series diverges. It means that you can't use the AST. Can't use AST, so we're going to use the divergence test, the DT. And I'll remind you of what that is. Hopefully you have your list of convergence tests somewhere close at your side and you can just glance at it. But it says if the limit as n goes to infinity of the terms an is not 0, then the series diverges. Okay, well, limit as n goes to infinity of the terms. Now I have to include the negative 1 to the n because the terms include that. So negative 1 to the n over n plus 1. The most I can say about that limit is that it does not exist. And here's why. Without the negative 1 to the n, we saw that the limit of that sequence is 1. So with the negative 1 to the n, what's going to happen is those terms are going to go bopping back and forth between positive 1 and negative 1. Half the time there'll be 1, half the time there'll be negative 1. And so that sequence does not have a limit because it needs to zero in on one single number. Thus, we can conclude that the series, the original series, diverges by the DT. All right, next set of definitions. A series converges absolutely. Sometimes I use CA, sometimes I use AC, shorthand, if the series of absolute values converges. So that makes good sense. Conditional convergence is a little more obscure. A series converges conditionally if it converges, but not absolutely. So this series diverges. So I don't think such a great name because it makes it sound like the series only converges under conditions, but that's not really true. If a series converges conditionally, it converges. It's just, it doesn't converge absolutely. And we have a very strong theorem that tells us if a series does converge absolutely, then you don't have to show it converges because it's automatic. So absolute convergence implies convergence. This can be confusing, I'll admit it. So that's why I have this flow chart for you. And you will be able to use this on tests and quizzes if we ever meet in person again. To determine if a series converges conditionally, absolutely, or diverges, you start to check for absolute convergence. Because if you have absolute convergence, you're done. That's the best. That's the strongest thing. And you can quit. If you don't have absolute convergence, then you need to put the -1 to the n back on and test the original series with the AST. If that series converges, then again you're done, because what you have is conditional convergence. That's the definition of conditional convergence. The series converges, but not absolutely. If that series doesn't converge, then you're also done. Everything just diverges. All right, so let's put this to work with some examples. This is a famous series called the alternating harmonic. Because it's a harmonic series, which is 1 over n, but it alternates, negative, positive, negative, positive. So step 1, this is the first step in our flow chart, check for absolute convergence. So when you check for absolute convergence, you get rid of the -1 to the n, and you just check the series that has positive terms, in this case, this series. And you want to state that that's what you're doing, and I did. All right, this series diverges by the p-test. P equals 1. So our series does not converge absolutely. Our original series, -1 to the n, 1 over n, does not converge absolutely. So have to keep going on the flow chart. Okay, so where we are on our flow chart is right here. So the next step is to test the original series with the AST. So now we're going to check -1 to the n times 1 over n with AST. And when you're using the AST, you always want to state your UN. UN is the sequence 1 over n. Okay. So there's 3 conditions, and they're just going to be no-brainers, so we can just put a check mark by each one. First condition, limit as n goes to infinity of 1 over n needs to be 0. Check. Nothing to show. 2, 1 over n is positive for all n. Remember, n is 1, 2, 3, 4, 5. Check. Nothing to show. 3, there's never anything to check for condition 2, by the way. It's always just going to be a check mark. 3, what's 3? The sequence 1 over n is decreasing. Check. Nothing to show. Numerator's fixed, denominator's increasing. So the series converges by the AST. And so what we say is that we have conditional convergence. Here's why. The series converges, the original series converges, but it doesn't converge absolutely. So when it converges but not absolutely, we call that conditional convergence. All right, another example. I'm going to do 2 more, and then there's some practice problems. We'll talk about those in a minute. So here's our series. The first thing we want to do in the flow chart is get rid of the -1 to the n and test for absolute convergence. So this is the series we're testing for absolute convergence. I can use any test I want. I'm going to use the ratio test. So rho is the limit. Again, pull out your convergence test sheet and take a look at the convergence test if you don't remember what it is. But rho is the limit of the absolute value of the n plus 1th term divided by the nth term. Now typically I'll multiply by the reciprocal, but in this case I'm not going to. 2/3 to the n plus 1. There's the n plus 1th term, and I'm dividing by the nth term. So n squared, whoops, that should have been n plus 1 squared. Sorry about that. N squared 2/3 to the n. Okay, everything's positive, so get rid of the absolute value. And I've got n plus 1 squared over n squared, which I'm going to write as n plus 1 over n squared. And then I've got 2/3 to the n plus 1 over 2/3 to the n, which is just 2/3. Now in the parentheses, I'm going to get infinity over infinity, so I'm going to divide top and bottom by n inside the parentheses. 1 plus 1 over n. Whoops, no, I don't need to do that. I'm sorry. Just write that as two separate fractions. N over n is 1, and then 1 over n is 1 over n. Okay, now the limit inside the parentheses is 1. 1 squared is 1. 1 times 2/3 is 2/3. 2/3 is less than 1, so the series converges absolutely, and there's nothing more to do. I checked for absolute convergence, it converged, and so on the flow chart, I'm done. Okay, the next one also converges absolutely, but I wanted to do it with you so that you could take a look at the factorial cancellation. So step 1, check for absolute convergence. So get rid of the -1 to the n and just check that series. And I decided to use the ratio test because whenever you see factorials, you want to use ratio. Here's the n plus 1th term, and I'm multiplying by the reciprocal of the nth term. Then I grouped terms that were similar. So I grouped the 2n plus 1 over the 2 to the n. I grouped the n plus 1 factorial, one of them, over one of the n factorials. And then I did that again. And then I grouped the 2n factorial over the 2n plus 2 factorial. That's what you see here. Now that's a step you could do mentally. I did it out so you could see it. But now you can simplify. 2 to the n plus 1 over 2 to the n is 2. That's where this 2 is coming from. N plus 1 over n factorial is n plus 1. And I get 2 of those. Those are in the numerator. That's where these two terms are coming from. And then in the denominator, 2n factorial over 2n plus 2 factorial is 2n plus 2 times 2n plus 1, because everything else cancels. All right, so let me erase all this stuff. So I'm right here. One thing I could do, this is infinity over infinity, I could multiply everything out and then divide top and bottom by n squared, but I can see a quicker way. This is the limit as n goes to infinity. Pull a 2 out of the denominator. So leave the numerator alone. Pull a 2 out of this first expression, 2n plus 1 times 2n plus 1. Now I can cancel the 2's and I can cancel one of the n plus 1's. And that's the limit as n goes to infinity of n plus 1 over 2n plus 1. Now I just have to divide top and bottom by n, and it's a little quicker. Limit as n goes to infinity of 1 plus 1 over n over 2 plus 1 over n, which is a half. A half is less than 1. So the series converges absolutely, and once again, there's nothing more to show. You don't have to do anything. Okay, so let me recap. The 3 cases are, you're going to get converges absolutely, that's the shortest. If you don't have absolute convergence, like example A, you need to check for conditional convergence. So after checking for absolute, you need to use the AST and check to see if that converges. If it does, we call that conditional convergence. And then if nothing converges, we just call that divergence. Okay, so I want you to stop the video at this point. Well, actually, you can listen to the rest of my talk here. I I got 2 practice problems here and solutions at the end. So you should do those without looking at your solutions, but then look at them. And I'm just going to walk you through some steps here. For the first one, the first thing you're going to do is check for absolute convergence and write down what you're doing. So you're going to check 1 over 2n plus 3. Now you can use any test you want. You could use comparison, or you could use limit comparison. Either one is going to show you that that series diverges. It diverges because it looks like 1 over n. So use limit comparison with 1 over n or comparison. I think in the solutions, what did I do? I used limit comparison. So that's not going to converge absolutely. So then the next step is you're going to have to check for conditional convergence with the original series. You're going to take the -1 to the n, 1 over 2n plus 3, and you're going to check that with the AST. And you'll see that that converges. And so this will converge conditionally. Okay, and then for the last one, the only comment I want to give you is that typically, we use the ratio test much more often than we use the root test. But on this one, when you check for absolute convergence, my hint is use the root test, not the ratio test. The root test will be much easier. All right, so I'll see you for section 10.7.